Okay. How about this one? Do you see the presentation?
Yes, everything works fine.
Okay. So the results that we are going to talk about today are form part of the project Trustworthy Distributed Learning, a TRURL for short, the friend of Klapautius. And this is a project that we have a collaboration with few institutions, but for our, like Krzysztof and I, a collaboration, most important link is with our friend Renata Cavalcante, who fortunately joined us today. So thanks, Renata, from Fraunhofer Institute in Berlin. And also Krzysztof collaborates with Professor Gabor from Maths department. So the four of us has developed some results that first me and then Krzysztof is going to present today, and they are part of this project. I am from physics department, Krzysztof is from Maths department, Renata from Fraunhofer, also Gabor Maths department. Okay. So my part is on fixed point analysis of non-negative functions and neural networks as functions. And this work has, the results has been obtained with Renata Cavalcante, who is an expert in wireless communications. So there are certain applications in this field, and also on optimization problems and on Perron-Frobenius theory, the nonlinear Perron-Frobenius theory that we have employed to some success in this in this line that I'm going to present. So there are two parts, because there are two papers submitted at this moment. The first one is on non-negative neural networks, and the second one on the convergence speed of the fixed point iteration of positive concave mappings. It turned out to be that the convergence of such fixed point iteration converges geometrically for such functions. And we do hope it is a result that has not been considered as a special case, for example, in literature before. But the first part is on neural networks, so on non-negative neural networks. So we would need to have some motivation, because always it is always encouraging to know that somehow it corresponds to the bigger reality outside this field. So it seems that the non-negativity, especially the non-negative neural networks, have made a comeback in some sense recently, but they have been used continuously since the resurgence of the neural networks in the 90s, let's say, because the non-negative input is natural in certain applications, which are very important, right? Because the neural networks work well on such applications, such as the image or text processing, where the input data is non-negative by design, by its very nature, and same for the spectral analysis, where we have the frequency profile of some signal. So the power on each band is non-negative by definition, by its physical property. So the non-negative inputs are omnipresent, we can say, and we don't have to somehow tweak the input in those fields to make them non-negative. They're non-negative by default, by the state of nature. Okay, so that's the non-negativity of the input, but how about the non-negativity of the neural networks? And by that, we mean that the parameters of the neural networks are non-negative. All the weights and biases are non-negative. And this recent resurgence that I mentioned before is in the context of analog neural networks, which I think for the last 1 or 2 years, maybe 3 years maximum, has made a big comeback because they work much more efficiently for a fixed task than a generic discrete neural networks, such as the neural networks we implement on our discrete machines. Okay, and for such analog neural networks, the parameters of those networks are non-negative, again, by the laws of physics, because the weights are encoded in the conductance of resistors that are programmable, so we can adjust them, just like we should adjust the weights parameters of the networks. And there's also one more motivation, which the fact which motivates our interest in non-negative networks, which is that because of the additivity property, because there is no subtraction, the weights are either 0 or positive, and same for the biases. So there is no subtraction. So the networks have been shown for the last 10 years, such non-negative networks, to be to enable understandable for humans and hierarchical representation of the input data. Because of the parts, for example, of an image that is processed, the image is processed in parts. And this is just like the human, the mammal brain is processing the sensory inputs, such as our eyes. They get the whole picture by merging the parts of the picture. I mean, the scene that's being seen. So that was these are the motivations that make the non-negativity analysis of non-negative neural networks of interest. And now the second part of the title, because we have a fixed point analysis of neural networks, of non-negative neural networks. So why fixed point analysis is important? Well, for quite a few reasons, but 2 of them are very easy to explain, especially for the autoencoder networks. The autoencoder aims to represent a signal, the input signal, in a compressed form, and then, for example, transmit it efficiently in this compressed form, and then decompress. So as a function, the fixed point set of such an autoencoder is precisely those inputs that can be reconstructed at the output without an error. That's the fixed point set. So we have to, if we ask ourselves which inputs are recoverable without an error at the output, then the answer is those that are in the fixed point set of the autoencoder. And also, if you look at the learning schemes that are used in the neural networks, which are mostly based on gradient descent, and the simplifications thereof, such as the stochastic gradient descent, which is just a special case of the gradients, but the paradigm is the same. It's just that the data used at each iteration is sampled. Then a lot of those, many of those methods can be cast as a fixed point iteration. Again, not only the gradient descent, much more sophisticated optimization algorithms can be cast as a fixed point iteration of a well-defined operator. For example, here we have the gradient descent type optimization. obviously the gradient is going to be 0 if and only if the operator in the brackets, the identity minus alpha times the gradient, this operator achieves the fixed point, the iteration which is the fixed point of this operator. And this is especially useful for approximating such iterations using neural networks, where each iteration defines a layer of a neural network, because obviously the iteration, however long, it is always finite. Right? We have finite steps of iterations, a finite number of iterations, which means that each iteration step can be cast as a layer of a neural network. And then the problem is to approximate the fixed point iteration using the neural network. So again, this is called the loop unrolling method. And again, now we have a problem how well the neural network approximates this fixed point iteration. So now we have a problem of finding a fixed point set for such a process. So now we have a motivation for both the fixed point analysis and the analysis of non-negative neural networks. And the model we use is a standard model. The default neural network model, the feed-forward neural network model, where we have n layers. So Ti are the layers of the network. And at each ith layer, we have an affine operator followed by a non-usually, but not necessarily, but usually a non-linear activation function sigma I. Okay, so we have an input vector x0, and this is processed by a network by composition of affine operator followed by the activation operator, and this is composed with subsequent layers. This is the most standard neural network model. And the first result that we obtain is that if the networks are non-negative, in the sense the networks have non-negative weights and biases, and for all standard activation functions that are used, such as sigmoid or ReLU or hyperbolic tangent, all standard activation functions, then the non-negativity, along with the such activation functions used, results in the network being monotonic and weakly scalable, or even scalable. Okay, this means that, well, the first definition is for monotonicity. Just please pay attention that now we are in the non-negative cone. So the inequality is taken with respect to a vector, which means that the definition is at the bottom right. So the u is less or equal than v in the sense of, in our sense. By definition, if v minus u, this vector, is inside the cone. For example, the vector 2, 1 is greater or equal than 1, 1, because the difference being the vector 1, 0 is inside the cone, is within the cone, not in the interior, but within the cone. But for example, vector 2, 1 is not in this relation with vector 1, 2, because the difference is not within the cone. So such networks are monotonic in this sense, and they're also weakly scalable or even scalable. So here we have a definition of weak scalability. So rho is some scalar here, and this basically means that the function doesn't explode, or it doesn't grow too fast. And actually, even we can have an even stronger result, stronger condition, that for certain activation functions such as sigmoid, or for certain scenarios such as a layer uses positive weights, so the weight matrix and the linear operator being the matrix at a given layer is strictly positive, the coefficients are positive, then we even have a stronger condition that the network is scalable, which means that yes, the definition is at the bottom, and the relation is that the right-hand side vector minus the left-hand side vector is in the interior of the cone. For example, 2, 1, vector 2, 1, and 1 and 1/2. The difference is in the interior, but 2, 1 and 1, 1, those vectors are not in this relation because the difference is not in the interior of the cone. Okay. We have a stronger condition satisfied under very mild assumption of the network. Okay, so that's the first result, and then since establishing this fact allowed us to use the concepts related to the nonlinear Frobenius theory to a nice to obtain some interesting results as follows. Okay, so first of all, let us consider the asymptotic mapping of a neural network. Right? The T infinity. That's if T is the neural network, then T infinity is defined by this limit. And since we know that the networks are monotonic and weakly scalable, the non-negative neural networks are monotonic and weakly scalable, then the result of Renato shows that the limit always exists, is well defined. Okay, so the asymptotic mapping is well defined in this case. And since it is, then also the spectral radius is well defined, which is the maximal eigenvalue of the asymptotic mapping, because the asymptotic mapping is shown to be also monotonic and homogenic. Okay, so the spectral radius can be defined, and this is the maximum eigenvalue of this asymptotic mapping. So because of the monotonicity and weak scalability of the network, we can define the asymptotic mapping because the limit exists. And we can define the spectral radius because the asymptotic mapping is homogenic and monotonic as well. And the second result that we have obtained is that the asymptotic mapping is, in the case of non-negative neural networks, not only homogenic, it is actually linear. And depending on the activation functions used, it is either identically equal to 0, or it is defined as a matrix being the product of matrices along the layers. The case of the asymptotic mapping being 0 is for the situation where at least one layer uses an activation function which grows slower, in the sense that the limit of the derivative of this activation function is 0, for example, a sigmoid. And the product case is obtained if all the layers use sufficiently fast growing activation functions, so that the limit of the derivative of all activation functions across the layers is non-zero, is mostly 1 for the commonly used neural networks, such as the ReLU or functions of such kind. Okay, so we have a very simple, this is the second result, we have a very simple form of the asymptotic mapping for a non-negative neural network. And then we obtain the result that establishes a shape of the fixed point set of non-negative neural networks, which states that if a neural network is monotonic and weakly scalable, which is satisfied for almost all, in well-defined sense, non-negative neural networks, and grows fast enough at the fixed points, then the fixed point set is an interval if the spectral radius is less than 1. And by looking at the expression of the asymptotic mapping, we can easily extract the spectral radius. Right? It's either 0 or is the largest eigenvalue of this product. Okay, so what does it mean fast enough? Well, fast enough means that in order to have a meaningful fixed point set for such a weakly scalable network, then the network must grow fast enough. Otherwise, the fixed point set can be arbitrary. And for example, I mean, we have some degenerate case where the fixed point set can be, for example, the whole cone can be the fixed point when you have some zero layer, for example. Not necessarily zero layer, but I mean, it's very simple to construct the identical neural network, right, that is going to have the fixed point set as the whole cone. But if it grows fast enough, then in the sense of upper and lower primitivity at these fixed points, this is some technical condition, then the fixed point set is an interval. And there's a simple condition, sufficient condition for this upper and lower primitivity to hold. And again, this is quite it's a natural condition for practically applicable neural networks to hold. So we obtained that the non-negative networks have a very simple shape, very simple expression for the fixed point set being the interval. We also have a stronger condition, a stronger result for the case of scalable, not weakly scalable, but scalable networks. This is a result from the paper of Renato and his co-workers from 2019. So if the network is even scalable, and again, we have the condition of the spectral radius being less than 1 that can be easily verified, then we have a if and only if condition, excuse me, for the fixed point set to be unique, to be a singleton. So the fixed point set is unique. So how it transpires translates to practical applications. Well, we considered an autoencoder case with 5 layers. So first we compress the input signal 180 coefficients. There are 180 because there are 180 degrees that the array is of the antenna array is sensitive to those angles, and we have a power signal, power spectral signal. So the non-negativity is by default assured, and that this is all standard in the sense of how the autoencoder is constructed and how it is trained. So one can just read the setup from here, but the important thing is that there is nothing special about it. Nothing special about it. It's just the standard non-negative autoencoder. Okay, so if we compress the input to the 40, the 40 to dimension 40, right? That's the compressed signal, and then out of the vector of the length 40, we decompress it back to the original the dimensionality of 180 coefficients of the vector. Okay, so we have the angular power spectra. That's what I said. The massive MIMO, which means that we have the antenna system, and we use the Adam algorithm. It worked better than the stochastic gradient. Again, everything is standard here. That's important because we wanted to show that the practical case that is used in industry with the standard setup fits to our model. Okay, and because we have, maybe let me go back to the previous slide for a while, because we have used hyperbolic tangent on some of the layers, which means that the limit of the derivative is 0, then the asymptotic function, we are in this case of the asymptotic function being 0, and the spectral radius is 0. So the network is scalable, and this means that such an autoencoder has a unique fixed point. So there's only one input that can be transmitted without an error, which is quite surprising, but that's how it is in practice. Yeah, that's how it is, and we have verified it. We have verified it in this example. So the unique fixed point is as follows. These are the coefficients, 180 coefficients of a vector. That's the unique fixed point. That's the only input that can be transmitted without an error, reconstructed without an error. So for all other inputs, the output is necessarily contains some mismatch. But as we can see, for this input in blue, which is very far removed from the fixed point, the unique fixed point of this autoencoder, the error committed is rather small. So if we go back to the analogy with the biological systems, you can say, such as processing of the sensory visual input by the mammal brain, that I haven't developed this concept. I'm citing the papers that have appeared in the last 10 years on the non-negative networks and autoencoders in particular. Then it might be the case that obtaining the perfect reconstruction is not the proper, is not the target cost function. Is not the target, is not the goal on its own. The goal is to have a non-negative network which allows to reconstruct a variety of inputs, but with a small error. We know that there is only one errorless input, but it might be very much the case that the non-negativity implies the robustness of the network, in the sense that even though the input is very far removed from the interval fixed point set or the unique fixed point set, still the reconstruction is sufficiently good. So sufficiently good may be sufficient, just like for our eyes, for the case of the image processing. Okay, and the other thing is to, so that's the open question. And the other open question is the question how to train smartly such non-negative networks, because at this moment we have used the standard ADAM. I don't know, maybe people call it also ADAM. ADAM training method, which basically projected the weights to the non-negative cone, which means that if the projection is very simple in this case, right? Because if some of the coefficients are negative, then they are projected, clipped to zero. That's obviously not the optimal way to do so. So training the non-negative networks, which has been considered in the literature so far, is also very much open problem, how to do it most efficiently, especially with the recent resurgence of analog neural networks. Okay, so the second subject, which is going to be shorter part, because I see this is 35 minutes, so I think this is going to be the shorter second part. It is shorter because basically we had one result to describe. Basically, we had a few results in the first part that led to the shape of the fixed point set of non-negative neural networks. Here we have the one result which is stated in the title of the work, which is that the fixed point iteration of positive concave mappings converges geometrically if a fixed point exists. As I mentioned, we very much hope this is a new result. We haven't seen that in the literature, and the reason for that may be that it is a special case that people, mathematicians, have not bothered, right? Because the mathematics always aim for maximal generality, and this is rather special result because we have positive concave mappings. So maybe this was fortunately overlooked. If not, then we can accept that. But if it is new, then it is going to be great. It is currently under review, so let's see what the reviewers are going to say. So why does it matter? We have also a strong indication that this result is new. So we are hopeful. And the reason we think that the result is new is that in 2020, a paper appeared that showed that in principle, the convergence speed of the fixed point iteration for scalable functions we cannot rule out the possibility of sublinear convergence for scalable functions. And concave functions are scalable, right? So the scalable is a superclass of concave functions. We are, of course, we always discuss in this my part of the presentation functions defined in a cone, the non-negative ortho in this case. Okay. So this was a negative result that we cannot rule out the possibility that for a given scalable functions, the convergence is sublinear. We have an explicit example or a counterexample for a scalable function. But the question is whether this is the same is true for concave functions. If we limit ourselves from scalable functions to a special class of scalable functions being concave functions, whether this negative result is still valid and it turned out to be invalid, because the convergence is not sublinear for positive concave mappings, it is geometric. I'm not going to show those this part because it is my co-author, Dr. Renato Cavalcante, is expert in the field. But this result is not only theoretical, possible theoretical interest, but it has very important applications, for example, in wireless communications, where the functions that are considered there are positive and concave. Okay, so just let me just briefly introduce what is meant by positive concave mapping. Please pay attention that, as before, the inequality is with respect to the non-negative cone, right? So so in both we have a vector value function. Okay, so the same definition of inequality applies as for the previous part of the first part of the presentation. Geometric and linear convergence, these are the definitions that I think that most of us are familiar with. Just please note that the linear convergence implies geometric convergence. Okay. So we used, since we are on the non-negative cone, we used the Thompson metric space, the Thompson metric that can be defined on each part of the cone. Clearly, the most of the one of most practical interest is the interior of the cone. So for this part of for the interior of the cone, we define a metric as follows in the red box, where we take the larger of the values of the capital M xy or yx. So the definition is rather clear, and then the log. And such a function satisfies the axioms of metric, and it actually defines a complete metric space on the interior of the cone. So we have a complete metric space. Just it is a metric space on the cone, so our standard imagination for a Euclidean space are not valid here, right? Because, for example, the set 0, 1 closed is in this Thompson metric space is closed and unbounded, whereas obviously for a Euclidean space it is neither closed nor open and bounded. Because for this metric space, the zero vector plays, you can say that it plays a role of infinity, right? So the closer we are to the zero vector, the farther we are to the infinity in the standard sense. But one result, because if we use the Thompson metric space, then the problem would be that the results are hardly interpretable for the practitioners, right? Because all since certain analogies do not apply, then it will be hard to imagine how it can work in practice, where in practice we have some metric induced by standard norms on RK. But fortunately, there's a key property that allowed us to translate the result from the Thompson metric space to the Euclidean metric spaces, the metric spaces where the metric is induced by the norm, which is that the set U in the interior of the cone is compact in Thompson metric space if and only if it is compact with respect in a space with a metric induced by a norm, arbitrary norm, the Euclidean norm or any other number, of course, all equivalent. So that's the key property, allowed us to prove the main result, and the main result stated here actually uses the fact that positive concave mappings are local contractions in the sense that on each compact set, right? So if you consider a function f defined on a compact set, and we don't have to care whether it's a Thompson metric space or the Euclidean space because they're equivalent, on a compact set, then it is a local contraction on the set. Positive concave mapping is a local contraction on the set, and this allowed us. This key fact was used to prove the main result, which is restated here. Okay, so the final thing is to check whether the theory works in practice. Study is not going to be invalidated by a numerical example, right? Because if it is, then it means that the proof is incorrect. So this is a slight variation on the very same example that has been proved that has been shown in the paper of 2012, 10 years ago, which showed that for general scalable function, we cannot rule out the possibility of sublinear convergence. It's just that for the interval 0 to 2, we have removed the definition 4 over 1 plus e to the power 2 minus x and replaced it with the identity function. That's the only difference. But Renato has found that actually this function is concave. It is a concave function, which means it's also a scalable function. So the slight variation on the example, on the negative example for the scalable function. This time we have not only scalable, actually concave function by this linearizing for the interval 0 to 2. So yes, so it is continuous and concave, and obviously the fixed point set is 0 to the interval. And let's see how the fixed point iteration converges. Let's say the starting point is at 4, right? Because the scalar function k is equal to 1 in this case. So it converges as follows. That's the ratio, and the ratio is basically 1 for all iterations, starting from second or third iteration, which means that it converges sublinearly, right? Because the ratio should be below 1 to imply not a sublinear convergence. If it is 1, then you have a sublinear convergence, which is a bit worrying. Also, the actual convergence to the fixed point set, to the fixed point set. Yes, we have 100,000 iterations. It converges very slowly, clearly sublinearly. So it appears that our result appears to be invalidated, right? Because we have sublinear convergence for a positive and positive concave mapping. However, there's another assumption that is not satisfied by this function. As we can see from the main result, the values should be in the interior of the cone. And this function is clearly not satisfying this property because the g of 0 is 0. So the result the main result of our paper does not apply to this function. So let's just tweak it to make this function satisfying all results, all assumptions of our result. So let us add a small positive constant. Here use 1,000 to the function. So then all assumptions are satisfied. The convergence is much faster. It is geometric by our result. And yes, 1,000 iterations are enough to reach the unique fixed point set in this case. The unique fixed point, singleton fixed point set in this case. So we verify by numerically verify yes, the result holds. So that's all for me. And now I think it is, thank you very much. I think it is Krzysztof's turn. So Krzysztof, I will stop sharing my screen now, okay?
Okay.
One second. Okay, stop sharing, very quick here. Okay.
Oh my God, I need to log out. There's
Okay, we wait for you. Out.
okay. So I'm here. I think you can see my desktop now. Sorry for the interruption, but the program needed some privileges to share the screen. Do you hear me? No. No.
Yes, we can hear you, Krzysztof.
Okay. So my presentation is a little bit smaller than Tomasz. I will present the results which we obtained with Professor Gabor, which are the extension or generalization of results presented by Tomasz. So let us start with the following example, the example of wireless communication. So so that it motivates us to use another assumptions we will see in a moment. Assume that we have n users, m base stations, and the power transmitted by the user j is pj. The gain of the user j to the base station k is hkj. Then the received power of user j is the multiplication of the gain and the power, and the interference seen by the user j. So the signals from the other users is the sum of the received signals plus maybe some noise. Yeah, and this noise, as you can see, it's in general setting, so it can depend on base station, it can depend on the user. And then when we have the power vector P, then the signal to interference ratio of user J is the multiplication of the power times this coefficient mu, which is defined here in the equation 1. So it is just the coefficient of the received power of user j to the power of other users. And there are many policies how to connect user to the base station. One of them is the minimum power assignment, which use the following rule. So we use for the maximum of this this signal to ratio times the power. and we assume that it's bounded from below by some constant. This problem can be rewritten in the following way. So we have the following inequality, yes, that the powers are less or equal than some function I, which depends on the user J, and is given here. Yeah. So in other words, or more abstractly written in the equation 3. So this is our motivation, which we will use in a moment, and observe that the maximum power of the best connection to the base stations is when the well, here we have equality, yeah, non-inequality but equality. Yeah? So this is the fixed P is the fixed point of the mapping I, and this model was abstracted or created by Roy Yates in 1995. He introduced the so-called standard scalable function, which satisfies that it is non-negative, it's monotone, and it's scalable. Yeah? So the conditions you heard about in the presentation of Tomasz. It appears that the standard scalable functions or mappings have at most one fixed point, yeah, and there is a trivial counterexample that they may not have a fixed point. But if we assume that the problem is feasible, so basically it means that there exists at least one x such that the f of x is less or equal than x, then the natural iterative scheme, yeah, so the natural iterative algorithm converges to a unit fixed point when we start from arbitrary power vector x0. Yeah, so this is the classical result from the seminal paper of Yates. And we thought about the problem presented there, and when I see the paper of Tomasz, I realized that when they approximate the interference mapping or the scalable interference mapping by some neural network, the assumption about non-negativity of weights or biases could look quite artificial. Yeah. So imagine that we have just a linear autoencoder, so we have linear layers, so that activations functions are trivial, so f of x is equal to x, and biases are 0. Then the process of training of such network is basically the algorithm called non-negative matrix factorization, which is not so trivial. And also generally, when we have a neural network, which could be a composition of several layers, the assumption about non-negativity of weights imposed on neural network may not be obtained naturally. As also Tomasz said, it's usually in practice is obtained by clamping or clipping the weights of the parameters of the neural network to 0 if they are negative. So it motivates us to consider the situation when the weights can be negative. So what is the first observation is that this function as a layer can be still positive in some way, can be still monotone, but the cone is not this positive alternate as it was before. It can be wider. Yeah? So there can be directions when the function goes below or goes backward. Yeah. So basically it's still somehow still somehow monotone, but in different way. And for that, let us recall the following notion. So we have a cone. The cone is a subset of Rn which is positively invariant, and the so-called blade is only singleton cone, which consists of 0. We assume that this cone is non-trivial. And having such cone, we can introduce the following notion, the order notion, yeah, the order relation with respect to the cone K. So X is less equal to X prime with respect to the cone K if this difference X prime minus X is contained within the cone K. Yeah? And similarly, we can define the strict something which is X is strictly less than X prime and X is strongly less than X prime. And following this, we can introduce the notion of monotonicity. So F is monotone or K monotone, yeah, with respect to the cone K, if we have the following relation. So if the arguments are in the order with respect to the cone K, then also the values of the function are following the same relation. So basically, in the picture, it looks like this. Yeah, we have arguments which are in the relation, and also the values of the function can be in the relation. Yeah, so this cone, as you can see here, is narrower than the natural orthant, but usually it can be wide. And in 2006, Harald Persson proved the following theorem. He assumed that the function is continuous, that the set of feasible solutions is bounded. Yeah, this S is bounded, and there exists at least one strictly positive feasible solution. Then, under these assumptions, as presented above, there exists one or more fixed point which is non-zero, fixed point of the mapping F. And when we look closely at the result, you can see that scalability is not needed here. Yeah? So basically, we use the notion of monotonicity. We use the notion of it's positive, yeah, function. So it's act from the positive orthant to the positive orthant, but we don't have a scalability assumption here. And the idea of the proof is as follows. We can show that there exists a small subset which is invariant with respect to the function F, and the topological degree on this set is plus minus 1. We can show using the assumption that the set S is bounded, so there is a big ball, let's call it dr, which contains this set S, and the topological degree on this set is equal to 0. Topological degree is basically a natural number which can be associated to some mapping and satisfies some conditions. I will not present it here, but it's just a tool which gives us the following result, that the topological degree on this strip here, on this lighter red strip here, is non-zero, and this gives us a fixed point in the set. Yeah? So this is the basic property of topological degree, that if the degree is non-zero, then there exists a fixed point in the set with respect to which we counted the topological degree. So this was the idea of the proof of Persson. And we look with Professor Gabor, look closely at the proof, and we realized that some of the assumptions are too strong. Firstly, we can see that the monotonicity is needed only on the set where there is no feasibility. Yeah? So this is the origin of this first technical assumption. And later on, we realized that also the monotonicity is not needed. We can replace it by monotonicity with respect to some norm. Yeah, this the so-called weighted maximum or supremum norm. So this is like generalization of this. A2 is generalization of A1, and if we simplify, so remove these quantifiers, we obtain the following A3 assumption. So we basically replace the monotonicity by the monotonicity of the norms. Yeah, so which is strictly better assumption. Yeah, it's than just typical monotonicity. And we also proved that using similar techniques, the following results can be generalized to the so-called guided function property, but maybe I will not say it into details. So we can focus on this A3 property, and in the picture it looks like here. Yeah, we have a value of the function f. If we wanted monotonicity, we will try to find the fx prime somewhere in the cone k. Yeah, but if we are trying to just realize what this assumption means, that it means we can lay this value of the function can lay everywhere outside this ball, which is derived by this norm, this weighted norm, as in equation 7. Yeah, and so this was the first generalization of the results we proved, and to present that it is not theoretical on the result, we found the example. The example is as follows: let alpha be a zigzag function as here. Then we can create a function f. Okay, at first it can look quite strange, but basically it's very simple. Yeah, it's a homotopy with joining point x, y with the point on the diagonal xx. Yeah, so we are going up, then the point from the diagonal is joined with the point yx, so we going backward, and then we go forward, and once again we go down. Yeah, so basically I will present you image of the mapping in a moment, but before we go there, we can observe that the function is not monotone, yeah, which can be checked by using the points 2, 0 and 4, 0 as arguments. However, it is monotone with respect to the norm. And what is interesting also that it satisfies the following relation. And the image of the interval from 0 to 20 looks like that. Yeah? So basically we can see, depending on the norm of point xy, it goes up and goes backward, forward, down, and so on. Yeah, so this is like the following line. if we replace the points x and y here, yeah, only here on the points which are the points to which we are approaching, by the values of basically any typical activation function, so sigma of x and sigma of y, then the function is also scalable. Yeah. And the second example, which gives us the possibility to check the condition A3, is this simple neural network. So we have activation function which acts on coordinates. We have the following matrix of weights, and biases are 0. Then the f, which is one layer of this function, of this neural network, is not monotone, but it is monotone with respect to the norm. Yeah. Okay, so having this in mind and these generalizations, we thought about what are the results which can be obtained when we take a wider cone, and for that we created the following cone. This is a cone which contains the vectors which are symmetrical with respect to the vector v, and the cosine of the angle between the w and v is less or equal than beta. Yeah, for example, for beta equal to 1 over square of 2, we obtain the natural monotonicity with respect to the positive cone R2. You should be 2. Yeah, this was the example of the planar cone. Yeah, so this cone generalizes the typical cones, and having this cone, we let's define the k-scalability as here. Yeah, so this is just a natural extension of the definition which was presented at the beginning. We proved that if the function is k monotone and k scalable, then it has at most one fixed point. Yeah. So this was the first result. The second result is if this generalization of Pearson theorem. So if the set S contains a positive x prime and f was as above, then there exists exactly one fixed point of f. And there was another result of us which states as follows: if we have 2 points, x prime and x bis in S, such that there exists another point which is in a relation with these 2 points, and we have like a change of direction of monotonicity of this f. Yeah, so the x is strongly smaller than f of x with respect to the cone, then there exists at least 3 fixed points. Yeah, and here's the example. Yeah? We have just a simple one, once again, one layer neural network with sigmoid activation function, and we check the assumptions. So there exist 2 points, and such that they are in the relation. So then there exists one point where there is a change of the direction of this function. So there must exist another fixed point in the interval x prime x bis. Yeah, so there are at least fixed points, and you can see them in the picture here. And also following the results by Tomasz and Renato, we proved another. This is the last part of my presentation. Another results which is generalization of the results. So assume that F is K contractive, which means that it's positive monoton, and it is contractive, but only on this vector V, which was the vector which was like, the axis of the cone. So we have contractivity, but only on this, within this direction, only in this direction generated by V. And then there exists a unique fixed point and natural iterative scheme converges to this point, and there is also estimation on the speed of convergence. Yeah. And this is all from my part. Thank you.
Thank you. Thank you for your talk. So now it's time for questions. So let us start the question part.
I have a small question, remark. Hello?
Please.
Yes, yes, we can hear you. We can hear you.
Okay. So, my remark is the following, because you know the notion of positivity you just used here. I mean, k-dimensional vector with non-negative entries can be in a natural way generalized in a non-commutative setting. When you replace such vectors by Hermitian operators with a non-negative spectrum, right? So my question for both of you is essentially, is it possible to generalize all these nice results in the non-commutative setting? Because also the sophisticated metric you use, I mean Thomson metric, this can also be generalized for Hermitian operators, Hermitian positive operators, which play actually key role in quantum mechanics. As far as I remember, this Thomson metric in the quantum scenario, it is usually called Hilbert metric. Okay.
Yeah. Tomasz, maybe.
I know that Tomasz is going to talk again next week in our group seminar, so we have an opportunity to discuss further this issue, but maybe you already heard or know anything about such non-commutative generalization.
As for me, I don't know the results, and I know that there are quantum neural networks, but I'm not familiar with them, and actually I don't know what is the role of non-commutativity there. So maybe it's crucial for here, maybe for having fixed points. I don't know that. Maybe I will need to read about that.
Yes, there's a book that we both read that has been recommended by Renato. I think Renato is also here. So Renato, if you want to add something, if you think it is important to add, then I would be very grateful. And the book that I am referring to is the book of Lemons and Nussbaum on non-negative, on nonlinear parent-Frobenius theory. They provide all the results for an arbitrary cone. So if you have a vector space, then we can define a cone, and there are no further assumptions. So our specialization to the RK is just because the networks that the neural networks that we consider are such, but in fact the results are applicable to, yes, arbitrary cones. And about the Hilbert metric, the Thomson metric builds on the Hilbert metric. It is the difference is that we have for each part of the cone, for the Thomson metric, we have a complete metric space. And the other difference is that the Hilbert space defines essentially points as classes of abstraction. So we have all the rays for a given direction within the cone. For the Hilbert metric, these are the classes of abstraction with respect to which we measure the distance, the metric. But for the Thomson metric, each element we measure the distances not between the classes of abstraction like we have for the Hilbert space, but we consider just points, the distance between points in the Hilbert space. And this is for us, yes, this is also more practical. Yes, because then we can translate those results easily to the Euclidean case. For the Hilbert metric operates, I forgot the word, but we know that it is possible, always possible, to use the classes of abstraction to define if unfortunately I forgot the word, but we have a space defined on the abstractions, on the classes of abstraction, not on the original cone, and then it would be less practical for us. But it is there is a very close connection, and it is clearly described. So in the book, for example, that I mentioned. So perhaps I can just present it more clearly, yes, on the seminar next Tuesday.
Thomas, I can add some stuff as well.
Please go ahead.
Okay, so I feel that for if you want to go to infinite dimensional Banach spaces or other infinite dimensional, I think the best book is not the one by Nussbaum, but by Krause. I mean, this mathematician. Yeah. Yes. Because most of the results in Nussbaum deals with finite dimensional spaces, but I mean they give pointers to the infinite dimensional case, the results. And I think that this Hilbert, you're talking about the Hilbert projective metric, yes?
Right.
Yeah, so this is the most useful to analyze normalized fixed point iterations. You have the, at least in communication systems, when you have the operator normalized by some norm. In this, this is a complete metric space if you take the intersection of the non-negative cone with the unit ball. And this intersection with this Hilbert projective metric is going to be a complete metric space. But I mean, and there are other metrics on cones as well, but this is well described in this book by Krause. But unfortunately, I'm not familiar with those other norms or those other normal vector spaces, because not metric spaces. Sorry, it's not a normal vector space. It's just a metric space, because I haven't seen many applications for communication systems. And that's my primary field of application of those results.
Right, so the quotient space, that's what I meant. But for the Hilbert projective metric, also I think that, of course, I can just go ahead with the Krause book, and maybe there's going to be some interesting points of thanks, Renato. And if it's possible, I will keep you posted. I mean, after the seminar with the group of Professor Chruściński, I will just contact so that we can see what can we do together, hopefully. But for the yes, it remains to be seen whether the infinite dimensional case is of interest, right? Because the Nussbaum book, it is an arbitrary cone on an arbitrary vector space, which is finite dimensional. I think that the finite dimensional case for I'm reading the book about the quantum now, and it seems that as far as the quantum computing is concerned, the finite dimensional Hilbert spaces are used there. So I will find out with the experts what they think about it on Tuesday.
Okay, thank you.
Thank you.
Thank you for your questions. And as Darek has mentioned, in next Tuesday we'll have a seminar in our group, and we will talk about this possible quantum generalizations. Seminar will be offline, so we'll just meet and discuss. So if someone would like to join, it is Tuesday 10:15 a.m. It's room 29 in the Institute of Physics. Just if someone is interested in. So thank you for your attention. And that's all for today.
Okay, so thank you very much for your kind attention as well. Krzysztof,
Yes, thank you.
you're there? Okay.
Thank
Thanks.
thank you.